All right, collectively we'll call these just the displacement. This is the displacement from the equilibrium position. Let me zoom in here a little bit. The displacement from the equilibrium position. That's equilibrium. That's if there are no forces acting on the spring, where the spring rests naturally, if you want to say it that way. And Hooke's law says that F, this force, is equal to negative K times X. Here, K is the spring constant. It just says basically how stretchy is the spring. If K is big, what does that mean? Does it mean that it's a really stiff spring or a loose spring? If K is big. Now, if K is big, that means that just a little bit of elongation or compression requires a large force. It means it's a really stiff spring. Yeah. So if K is really big, that means it's a stiff spring. So like the springs on your car have a really large K because they're very stiff, but the springs are like a slinky or whatever, big or small K. Small K, right. So it's a really loose spring. It doesn't require much force to elongate it or compress it. This negative, described here. So let's say that we have a spring. This is its equilibrium position right here. At this point, it's at equilibrium. I pull back on the spring. I have a mass attached to it, and I pull back on it, and that elongates the spring. Is that going to be a positive or a negative X? I have an X in this direction. Is that positive or negative? That's a positive X. My displacement is in the positive direction. So this is the force on the spring. Is it in the positive or negative direction? It's the negative direction. So if I think about springs, if I pull them away from the equilibrium position, then the force of the spring is going to be the opposite direction, because it always wants to return to that equilibrium position. And that's where that negative comes from in Hooke's law. This F equals negative Kx. This just denotes that the force is always opposite the elongation. Actually, I think I write here. So here, this force from the spring is always opposite the displacement. The spring wants to return to its equilibrium position. The spring doesn't want anything, but you understand what I mean, the forces and the way that they act cause it to move back to that equilibrium position. Like to say that the spring wants to return to its equilibrium position, that would be reminiscent of who? Who would say that? That we talked about. Aristotle, very good. So he would say that the spring has its natural state. Let's see, I have a little clip here. This is just about the Royal Academy. This was during the time of the Enlightenment, time of Newton and Boyle and Pascal. Well, Pascal was a little bit before then, but it was really the birth of modern science, especially in England, in the Royal Academy, which was there. That was really a center for a lot of the new science that was being done, and really the beginning of how we think about the world. That is, that you can take the world and you can observe it, and you can begin to discern how the world works. And this is just sort of what it was like then. It's a guy that wrote a book. It's not really about the science of the time, but just the history. I think it's fairly interesting. So this is just sort of for your own interest. They sort of had a contentious affair, Hooke and Newton and others, and they talk a little bit about that. So this is just, I thought that was interesting. All right, let's look at some conservation of energy problems regarding this. So let's say that I have a spring, it's in its equilibrium position, and then I have a mass, and I'm about to push it up to the spring. At this point, none of them have any energy. The block's not moving, it has no kinetic energy, the spring's not compressed or elongated, so it has no potential energy. However, if I take this and I compress the spring a certain distance x, then I've given this spring elastic potential energy. and that elastic potential energy is equal to 1/2 kx squared. I'll show you how we derive that in just a bit, and then we'll use that derivation to work through some other problems. But that potential energy is 1/2 kx squared, and the kinetic energy here is 0. So this system has only potential energy. But if I release the system, all of that potential energy is released into the block, and it gives it kinetic energy equal to 1/2 mv squared. Now, just as we did with the gravitational conservation of energy problems, we can say that the total energy here is equal to the total energy here. And so we can then claim that the 1/2 kx squared in potential energy is equal to 1/2 mv squared in kinetic energy. And just as we did with the gravitational potential energy problems, where we did like the roller coaster type problems, we can figure out what are the velocities or positions of these objects at particular points. We can determine this work done by the spring by summing up the product of the force and the displacement over a certain interval. So if we want to know the work done by the spring, remember that's just going to be F times X. But I want to take, if my force now is dependent upon the position as it is for the spring, because the force of the spring will be dependent upon what is the elongation or the compression of the spring. And what I have to do, if I want to know the work over a certain displacement, is I have to take a summation over that force times the displacement. And for every interval that I sum up, my force is going to change. And we have a tool that we can use to do the summation. It's called the integral. And so we can find that the work is equal to the integral of F times dx. So remember, integrals are really just summations, right? When you learn the definition of an integral, which you aren't taught one now, but next semester when you learn the definition of an integral, it's really just a summation, right? In particular, it's what of a function. Like if I were to plot the force as a function of x, and it looks like this, and I want to take the integral over a certain interval of that function, what does that tell me about the function? Right, so just like we did before when we were trying to find the distance, we could take the area under the v versus t graph, and that's just the integral. So the integral, if I want to take it over a certain interval, is just the area under that function. So it's nothing fancier than that, but it involves limits as well, because you let those steps go down to an infinitesimally small value, and so you get an actual value for the integral. All right, so I want to take the integral of f dx. All right, so if the work is equal to the integral of f dx, my force here is a function of x, so it's negative kx times dx. All right, so I can take the k out because it doesn't depend upon x. So I have negative k and the integral of x dx. Now what is the integral of x dx? All right, 1/2 x squared. Remember the integral of our polynomials, let's do like ax to the n dx. If you remember this rule, it was ax to the n plus 1 over n plus 1. You'll need to know how to find the integral of polynomials. That's really all we'll do right now. Later, when we get into oscillations, we'll do integrals of trigonometric functions. But for right now, I just need to know how to do the integrals of polynomials. All right, so this then is negative k times x squared over 2. And so if I rewrite this, I get the negative 1/2 kx squared. And then the elastic potential energy is the negative of the work that's done by the spring. So if I want to know the elastic potential energy, I'm going to give it a subscript s for the spring. It's going to be the negative of the work that's done by the spring. And so that elastic potential energy is equal to 1/2 kx squared. this term, that the potential energy is equal to the negative of the work, this also carries over. You might find this a little more easier to understand when we think about it in terms of gravitational forces. So remember we had before, when we had a block, we were considering moving from this position up to this position. All right, you have two forces acting on it. You have the force that you're pulling up on it with, and then you have the force due to the weight, the gravitational force. In this case, does the gravitational force, as this block moves from here to here, does the gravitational force do negative or positive work? It does negative work because the force is down and the displacement is up. So in this case, the gravitational force does negative work. But I know, as we found previously, that the potential energy up here is equal to mgh. So the work done by the gravitational force is going to be negative Fw times h, or negative mgh. And yet I know that my potential energy is equal to mgh. So the potential energy doesn't have a negative value. All right, the point of this is just to show you that the work here, or the potential energy rather, is equal to the negative of the work. It's not terribly important right now, but just sort of to clarify. Is that clear? Sort of? As mud? All right. All right, let's do an example problem. I should do this one first. This one's pretty simple, multiple choice question. Here I have a spring. It's compressed by 20 centimeters, and then it's released. And I just want to know the velocity of the block when it passes through the equilibrium position of the spring. You want to think about the potential and the kinetic energy and where it contains those values, where potential is 0, where kinetic is 0. There we go, shoot for about 20 more seconds. I will stop at 3:45, 3:45, 10 more seconds. Just guess if you don't know. A few more seconds. Alright, B is right. Very good. So here, at this point, I have potential energy, but my kinetic energy equals 0. My potential energy is 1/2 kx squared. And at this point, where x is equal to 0, my potential energy is equal to 0. It's at the equilibrium position, so the spring contains no energy, right? But it does have kinetic energy, and that's equal to 1/2 mv squared. So the potential energy is equal to the kinetic energy. The halves cancel. I'm solving for v, so that's going to be the square root of kx squared over m. And if I put in those values, I get 6.9 meters per second. Being careful here because this is in 20 centimeters. Often when we talk about a spring compressing, springs aren't real big for the most part, so we won't talk about them compressing in terms of meters, but in centimeters. So be careful when you see these problems because the elongation or compression might be in centimeters. So I convert that to meters, and of course that's 0.2 meters. Alrighty? You can see a problem like that. It could be also paired with an interplay of gravitational potential energy and kinetic energy. I have a little video clip here that sort of talks about this. This is from the PBS series on the circus. Have y'all seen this reality show about the circus? It's online. It's actually fairly interesting. It just follows a circus, but as they go through, they did these extra little clips about the physics of the circus. I think the reality show is more sort of like reality shows where they talk about, you know, who fought with who and whatever. So, but they have these extra clips about the physics of the circus. And this is talking about this acrobat, this Eastern European lady, I'm not sure where she's from, but she does this routine where they bounce her up in the air. It's really pretty spectacular. Well, let's just watch for just a second. What is the initial energy of the block? Holler out when you get it. It's all kinetic energy, by the way, right? I have it. This block's moving along at 12 meters per second. Courtney, you have it? Okay, what do you think?
I got, well, it's the kinetic energy, and that's 230.4.
That's right, 230 joules. So my initial energy is all in kinetic energy, and that's equal to 1/2 mv squared. And that's equal to 1/2 of 3.2 times v, which is 12 squared, and that's equal to 230 joules. All right. Now the next part of the question is a little more complicated. I want to know what or how far does the block slide before coming to rest. Now, this frictional force, or this force that's described by this function, this negative 3x cubed, is this doing positive or negative work? Now notice the sign on this. The sign of this is negative. That means that that force is always going to be in the negative x direction. So is it doing positive or negative work? It's doing negative work. So it's acting to give energy or take away energy from the object. it's acting to take away energy. So what you want to do here, and I'm going to give you a couple minutes to think about how to do it, but is I know that I have this amount of energy right now, right? And I know that this force is taking away energy. I want to know how far does it go before it takes away all of this energy. So what you need to do is to calculate the work done by this force, and then solve for the final position where all of that work, that is 230 joules, has been taken away. So how do I find the work done by that position varying force? How do I do that? Remember when we did this with the spring, we said that the work was equal to the integral of our force that varies with position with respect to dx. So you want to take the integral of that force with respect to dx and then solve for our final position when our total work is equal to 230 joules. Give it a go. I'll give you a little head start. I'll come after you. When you're doing that, I'm going to look ahead for just a second. So I'm going to take this away. What is this integral? Negative 3x cubed dx. What's the result of that? Right, negative 3/4 x to the 4th. That's the x to the n plus 1 over n plus 1. And then that's going to equal negative 230. All right. Now, don't forget that you have to evaluate the integral at its initial and final positions. So 0 to xf. And then you want to take that and solve for xf. So you see this force, which varies with position, is taking away energy. And I want to know how far it goes. Anybody have an answer yet? You have it, Harley? 4.1, is that, yep, 4.2. Other folks get that? I don't know what the answer is right now. Yeah, you all agree? All right, so let's see, I have negative, actually I'm going to get rid of that negative 3/4 xf to the 4th power is equal to positive 230. Just made both of those negatives positive. So xf is equal to 4/3 of 230, and raising that to the 1/4 power right, or to the 0.25 power. And what did you say it was already? 4 point something? 4.2 meters. So that means that this object, which is traveling along this plane, which has this variable force, will travel 4.2 meters. Can I go down from here? Let's look at a couple other sample problems. We have a little bit of time left. So let's look at some other sample problems in the back of your book on old exams. Can I go down? So we look in the back of your book. Let's see. Quiz 3 or exam 3. I used to call them quizzes. Would that make y'all feel better to call them quizzes? No? Okay. Let's see. This is a very good problem. I mean, you could do this from a kinematics perspective, but it's a heck of a lot easier to do this from an energy perspective. So here I have an object that's sliding down an inclined plane, and first I just want to know if I just imagine that the plane is frictionless, that there's no forces opposing the motion, and then and I ask what is the speed at different points. Now, as I said, you can find out all the forces and draw your vector diagrams and figure out that the component of the weight is actually pulling this object down, and then you can find its acceleration, and then you can figure out, well, what is its velocity? But it's really simple to just apply our conservation of energy. At the top, it only has potential energy. At the halfway point, it's half potential and half kinetic. All right, because I've reached half of my total height, right? Like the girl with the basketball hoop. Remember at the basketball hoop, which was the halfway point, she had half kinetic and half potential. And then at the bottom, it's all kinetic, so it's only kinetic. All right. So at the top, if I'm looking at part A, I can find that the potential energy is equal to mgh. And part A asks for the speed at this point. And so I'll come down here for part A. I will say that the total potential energy is equal to, this is at the top, I'll call it T, is equal to the potential energy at point A plus the kinetic energy at point A. Could y'all just a second go ahead and find the velocity at that point, or the speed at point A? How fast is the object going when it reaches point A? By the way, it's on page 320 of your book. I get 5.5 meters per second. Y'all agree? Is that what y'all got? Let me step you through this. So I say the potential energy at the top, that's all that it has at the top because it's not moving. That's going to equal to the potential energy at point A plus the kinetic energy at point A. The potential energy at the top is just equal to mgh. Now this h is going to equal 3 meters. That's the total height. The potential energy at the point A, which I say is halfway down, is going to be mgh over 2. H over 2 because it's halfway down the inclined plane. So I'm now not at 3 meters, but I'm at 1.5 meters. But I just leave it in terms of h for a minute. And then plus 1/2 mv squared, that's going to be the kinetic energy at point A. All right? And then I can solve this. I take my mgh over 2 over to the left-hand side, and that just becomes mgh minus mgh over 2, or mgh over 2. Cancel out my m's, and solve for v. You get 5.5 meters per second. What if you wanted to find the velocity at point B, down at the bottom? Then I would say mgh at the top is equal to 1/2 mv squared. Go ahead and solve for that. Yeah, Chase?
Kinetic energy at point A would be 1/4.
1/4 mv squared.
Because isn't kinetic energy 1/2?
But you're right that the kinetic energy is half of the total energy, but your kinetic energy is just, oh shoot, that's a good way to explain that. I understand what you're thinking, but it's not the right way of thinking about it. Your kinetic energy is half of the total energy, but this value right here represents half. Like your ball is going to have a certain speed, and it has a certain mass, and so the kinetic energy is going to be 1/2 mv squared. But it just so happens that because this is half the total energy, that this value is also half. Because you have half plus a half. Okay. Does that answer your question? You're not going to put in a fourth. The only reason I put in this half here, I didn't put a half of the potential energy. The only reason I did this 2 here is because I was at h over 2. That was my position. I could just as well just put, 1.5. All right. Now let's see, in part B, if I want to know the speed at point B, I do this. I cancel my m's. V then is root 2gh. 20 times 3, root of 60. 7.7. All right, so that takes a fairly complex problem if you look at it in terms of forces and Newton's laws, and makes it very simple, just simple one-step problems that you could do in terms of kinematics, but become a lot easier in this way. All right, part 2 is similar to what we had previously. I'm going to erase what I have down here. Now, erase all of it, is that okay? Here we say that we have a force that is variable with position. Very similar to what we had before. And I want to know the speed at the bottom of the plane and how much work is done by the force. Right, so this is my force. If I want to know the work done by it for part A, I just do the integral of f dx. That's the integral of negative 2x dx. What is the distance over which it's acting? So if I'm going to evaluate this integral over particularly from an initial position to a final position for x, what are those values that I'm going to integrate it from? From what to what? How far is it moving? Not 0 to 4. I understand why you're saying that, because I have this 4 meters. But remember, on our inclined plane, we let this be our x-axis, and I have that marked here. And this is our y-axis. So I'm moving from here down to here. This is x equals 0, and somebody said it. What's my final position? It's 5, right? X equals 5. This is a special 3, 4, 5 triangle. All right? All right, so x equals 5. So I'm integrating this from 0 meters to 5 meters. That's going to be the integral of negative 2 x squared over 2. Twos cancel. That's going to be negative 25. So the work done by that force is negative 25 joules. Now, that means that it takes away 25 joules of energy as it moves down the inclined plane. So if I want to find the speed, what am I going to have to do? I know the total energy at the top. What do I do, Sean? Now, what is the final answer here?
It is 7.4.
7.4. And remember before I had 7.7, right, was the final speed. So it's going more slowly now. And the reason it's going more slowly is because it has less kinetic energy. So what am I going to do with this value to find the total energy at the bottom? Michael? You were about to say it, I know. Hunter? Okay, I say that the kinetic energy, or the, no, not exactly. Set what equal to the kinetic energy? Look, it has a certain amount of potential energy at the top, right? That's the total amount of energy. But I'm taking this much energy away from it. So I'm going to say that potential energy, the total energy at the top, minus 25 joules will equal the kinetic energy at the bottom. And the potential energy at the top was 10 kilograms times 10 meters per second squared. That's the weight, or mg, times h. What was the height? 3 meters. Minus 25 equals 1/2 of 10 kilograms times v squared. And I solved that for v. It's 100, 300, 275, 4, 550, 5.55. Is that right? 55? Yeah, so v turns out to be the root of 55, which is 7.4 meters per second. So that force has taken energy away from that object and causes it to go at a slower speed than if that force wasn't there at all. Very likely to have a position-varying force, of which you have to find the work done by, something similar to this. There are some other examples in the old test if you want to look at those.
For position varying, we always take the integral to find the work done.
Right, to find the integral, or to find the work done, the work is always going to be the integral of f dx, and the integral of f dx.
So why don't we have to consider about the work done by the gravitational force, put the work done by gravitational force in the equation?
Whereabouts? Here? Like in this last part that we did? Well, you are considering the work, right? Because when you include this potential energy, if I think I understand your question, that potential energy does include the work. That is the work. You did a certain amount of work to move it up to that position, and you changed the gravitational potential energy of the object. I think that's the answer to your question, if I understand it correctly. All right, guys, we're going to move on to momentum next time. If you all have some questions, we can spend some time in the beginning covering those. But I think we're pretty much wrapped up with this. Work of a position-varying force, and conservation of energy. Those are really the major topics in this chapter. The homework will help you as well, so please take a look at that. You should have hopefully already done the homework, but if you haven't, do it in the next couple of days before we meet next. I'll see you on Friday. Great day. Clicker this